what? 50,000 square kilometers, and is Greenland bigger or less?
What's the question?
Bigger.
Watch out, you got some crazy.
We'll take care of it, don't worry. That'll only be 11 points off your score. So yeah, basically, it's an ice sheet. It would be an ice cap if it were smaller than 50,000. Okay. So let's think in terms of these two types of landscapes that we're going to develop. One is going to be erosional, and one is going to be depositional. And they're going to really look different. So let's kind of look at the erosional landscape first. Here you can see where the glacial ice has moved across the bedrock. And look at the striations or the grooves that it's left. Both of those are official terms. Usually when they're big like this, they're called grooves. And when they're just kind of streaky like this, they're called striations. And it's the ice moving across the bedrock. So the striation is going to be parallel to the direction of the ice flow, isn't it? Here's the problem, though. Remember back in mineralogy and lab, you learned that the harder mineral scratched the softer mineral? Okay, so I've got ice moving over the bedrock leaving these striations. What's harder, ice or granite? Granite, by far. Ice is maybe a 2 to 3. Well, here's what's going on. The ice is picking up debris that it's going over, whether it's loose gravel or it's kind of pulling a piece of rock out of the bedrock. But all this material now is in the base of the glacier as the glacier moves along. So the ice isn't leaving these scratches. What's leaving these scratches, it's all the debris that's in the bottom of the ice sheet. It's other pieces of granite, other pieces of bedrock, other materials that are a heck of a lot harder than ice. So the ice is using this debris as a tool to make this striation. Eventually this debris is going to get ground down, isn't it? And new debris will be picked up and carried along and do the same thing. So it's an ongoing process. What if most of the debris was sand-sized material? Would that do much for striations? Well, kind of think in terms of scale. Let's say most of that debris is quartz, and it's all just sand-sized quartz. And I've got this pressure melting at the base of the glacier, and it's mostly water with this sand-sized quartz mixed into kind of a slushy, pasty material. And I'm scraping that along the bedrock with all this overlying weight of glacial ice. What's that going to do to the bedrock? That's just like a big polishing wheel, isn't it? Polishing is just finer and finer scratches to where they're so small that it takes on a lustrous surface. So now instead of leaving big grooves and big striations, they're fine, and I'm going to polish up the surface of that bedrock just like somebody had come through with a big grinding wheel and a polishing wheel and turned it into a shiny floor. So it's all just kind of a matter of scale, but the same process is going on. Now, if I look at those striations, I know which way the glacier went, right? Well, I know two of the ways the glacier could have gone. It's going parallel to that striation, so it could have gone this way, or just as easily it could have gone this way, right? I know the bearing, but I don't know the absolute direction. But here's something I can look at that gives me that absolute direction. And it's called a Rochemont. These are really kind of cool. It's this asymmetric bedrock hill. And notice, this is bedrock, it's an erosional landform. That's a point to note because we're going to come back and look at a depositional landform that looks similar to that tells you something different. And you can see a couple of them here. Striations, so you kind of get a sense of the direction. But notice the asymmetry. I've got this real gentle slope, and then all of a sudden, it just falls off. Steep slope, rubbly, chewed up. Well, what's happening is the glacier's coming along and it hits this bedrock high. And that slushy, sandy material at the bottom, it just polishes and grinds its way up that face of that bedrock high. Pressure's increasing, isn't it? Because now all this ice has to get up over the hill. It's slamming into that hill. Pressure's increasing. So I'm starting to melt the bottom of the glacier. And as that glacial ice melts, more debris coming out, and that just acts as a big grinding wheel as it moves up the slope. I get to the top of the hill, and what happens? The ice goes over the hill, and then it kind of goes, oh, wait, there's a hill here. Where's all that pressure that I ground my way up through? Now it's done. And now, if anything, the ice, instead of compressing to get up over the hill, can start to expand out again. So pressure's dropped. Everything's going to start freezing up again. So up here at the top of the hill now, any water that was in the cracks in the bedrock, it can freeze up. And as it does, it expands. Mechanical weathering going on. The moving ice freezes to the rock, pulls it out of the cliff, and carries it away as part of the basal debris in the glacier. It's a process called plucking. It's like you pluck feathers out of a chicken. And sometimes it's called quarrying because it looks like people came in and were actually running a quarry there at one point. But the net effect is you get this gentle slope where it's beautifully polished, braided, and then you've got a cliff, drops down, and you've got all the blocks sort of just pulled out of the bedrock, carried away, little debris left behind. So you've got this asymmetric, polished, plucked slope. It tells you which way the ice was going, doesn't it? Ice was grinding its way up the gentle side, moving away, pulling the bedrock off out of the quarrying side. You've got an absolute direction indicator now. So if ever I see one of these, I know which way the ice went. Way better than just having striations. Okay. Striations display a compass bearing or a line of glacial movement, whereas Roche Mountainais display an absolute direction. I'm only going to give you 15 seconds. I know you all know this.
Oh, it's not.
15 seconds, all right. Ooh, got one person.
Trick them.
I think that was that one person who kind of says, oh, he thinks he knows that we all know this now. So okay, absolutely. Glacial striations are great, and you got glacial striations all over the Roche Mountainais, don't you? So that's giving you the bearing direction. But that asymmetric Roche Mountainais shape tells you the absolute flow direction. Okay, so where do glaciers start? Up in the mountains. And as I start, I'm going to start collecting snow. I'm going to see that snow accumulate, compact, recrystallize into ice. So here is an area that is the beginnings of a glacier. This is what's called a cirque. And a cirque, so like circus, Cirque du Soleil, cirque, it's this big bowl-shaped depression. Notice how it's even kind of bowl-shaped downward, has a lip out here. You can see one here with snow in it. And this is where the head of the glacier is. This is where it begins. And as the glacier accumulates and moves material out, this cirque is going to expand as the snow moves the debris out of the cirque. It means the cirque's going to move headward and outward. So here I go. I start moving glacial ice downhill from the cirque through the valley system. Everybody know what this is? Matterhorn. Yeah. Pretty famous mountain, isn't it? The Matterhorn is actually the remains of 4 cirques. You know when we looked at Tower Karst and it was just the bedrock that was left over after all of the sinkholes and everything else away? Well, this is the bedrock that's left over after the cirques have eaten away all the bedrock surrounding. You can see this is the head wall of the cirque here, another cirque head wall there, one along there, and it's hard to see, but there's one on the back. So 4 cirques were eating their way headward, and they came together, and this is the remnant that's still left between those 4 cirques. This is called a horn for obvious reasons. It looks like a horn, right? The shape of a horn. But this Matterhorn is actually the Matter Mountain. And it's the Matter Mountain horn, but everybody has shortened it and just calls it the Matterhorn, and now everybody thinks that's the name of the mountain. It's all one word. It's actually 2 words. So, here's the beginnings of a glacier. You can see a couple of these cirques right here. Here's one here. You can see the head wall here. You can see this ridge out here. Notice it's got a lake in the bottom when it's melted. And that's known as a tarn lake, T-A-R-N. And here's another cirque, another tarn lake there. And notice that as the cirque has eaten sideways, that the wall surrounding this cirque and this cirque is disappearing. It's kind of being eaten away from each side. But look what's happening to the shape of this thing. Look at this thin ridge line right along here. It's just like a razor-sharp serrated knife blade almost. Cut up this way, cut up this way. And that is known as an arête. So arêtes are basically cirque walls between cirques, razor-sharp type of landforms. And you can see a horn back here, another one over here. You see another cirque back over here. You can see this whole mountain system back here is just a whole series of cirques, arêtes, horns, all feeding glaciers. Now, this is a picture of the heads of valley glacier systems. And this is from Pakistan. And this is the Pakistan-Afghanistan region where they originally were looking for Osama bin Laden. And you can see why they were having a little trouble finding him. Can you imagine getting around in this kind of terrain? You kind of have to know where the secret pathways are. It's pretty rugged and pretty difficult terrain to get around in. Now, when we talked about rivers, and we talked about the early stages of rivers, we said rivers tend to be cutting downward, and they make these V-shaped rivers. V-shaped is kind of the way rivers look most of the time, until they get to old age transportation segment where they have big floodplains. But if you're up in the mountains and you're looking at a river coming through a mountain, you're going to be looking at a V-shaped kind of valley system. You can just see it right here. But use this to funnel ice down through the system. And the ice is going to start to erode it out. It's going to widen it, it's going to smooth it. And by the time the ice is done, it's going to be a gorgeous U-shaped valley. No more V-shape. Beautiful, smooth, U-shaped valley. And notice in this one, it's a huge valley. And look at this crummy little river. There's no way that little river cut that big, huge valley. And there are no floodplains, there are no terraces, nothing. That river is kind of a remnant of what really cut that river in that location. So whenever you see a U-shaped valley like this, you should just automatically glow, glacier. That's the immediate thing you ought to jump on. Now, let's look at this. This is kind of cool. Let's start with this topography. I've got a main channel here where the river is flowing through, and I've got a few little tributaries kind of going up into the highlands. Now I've got a glacier that comes through. And immediately, the main trunk of the channel is going to be the main place where the ice is going to be flowing. It's going to be gravity driven, so it's going down through the lows, right to the main channel. And the tributary channels, well, they're also going to start to fill in, and the heads of those tributaries are going to become cirques, and they're going to be cutting headward, but they're nowhere near as big as the main valley, and the glacier is really scouring out that main valley and really expanding it. The little tributaries, okay, they're expanding too, but nowhere near as fast as the big main valley. So now, when all the glacier is melted and the drainage system reestablishes, look at what I've got. Instead of a V-shaped main valley, I've now got a huge U-shaped valley with a misfit stream, a little stream, and all the tributaries, well, they're U-shaped too, but they didn't erode as fast as the main channel, so they aren't as deep. So now, instead of seamlessly flowing into the valley like they used to, now they're up here, the main valley's cut deeper, and I've got a series of these little U-shaped valleys high up on the wall, and we call those hanging valleys. So anytime I see this, man, I just look at this and I go, okay, there's the main glacier coming down there, there's a tributary used to hanging valley, look at the arêtes, the horns, look at the cirques, tarn lakes, and I've got a bunch of tarn lakes up through here. So you can just kind of see, well, that's where the cirque used to be, and then it ate back here, and it sat here for a while and made another tarn lake, ate back here, made another tarn lake. So I've got this string of tarn lakes up along through the valley system. A couple of beautiful pictures here. You can see the U-shaped valley coming down into the main valley. That's basically Bridal Veil Falls out in Yosemite. Beautiful picture. And again, same kind of thing, just on a different scale. So true or false? Horns are the erosional remnants or three or more arêtes. Remember what an arête is. Seconds. All right. It looks like people are kind of leaning toward the false side. Well, here's the Matterhorn. And we said this was the result of headward erosion on the cirques, and I had 4 cirques that made this horn. But I could have made it with 3 cirques, couldn't I? I'd still have a horn sticking up there. So 3 is the minimum. I could have had 5 or 6, but 3 is the minimum. If I had 2, so it was just eroding up this side and this side, what would I have? I'd have a linear feature, right? And that would be an arête. So I wouldn't make a horn with anything less than 3 cirque directions. I've got to take that arête, which is along linear, and I've got to chop it to just a point. So the arêtes are the basic remnants wall-wise. So if you look at it, there's an arête, this edge is an arête, that one is, there's another one on the back. So I'm seeing the walls of the cirque coming up, and I've got arêtes that are sticking out, making these sharp angles of the horn. So I gotta have at least 3. Three circles.
Is that true?
So this would be true.
That's true.